Afternoon. There was an interesting article yesterday in the newspaper, well, an obituary. I just thought I might draw it to your attention. Scientists that transformed the study of memory, Endo Tulving, 1927 to 2023. Endo Tulving, who transformed the study of human memory with revelatory observations about how the brain stores and retrieves information. For example, differentiating from knowing what a shoe is to remembering the purchase of limited edition Nikes. Died September 11th at a retirement home in Mississauga. He was 96. Tulving, a cognitive psychologist who taught at the University of Toronto for 35 years, almost single-handedly pushed his field to think of memory as something more than just one big pile of information, memories and experiences. His peers recalled him as a towering figure in psychology and neuroscience. The two forms of memory that he described, he picked out, were semantic memories. For instance, knowing that George Washington was the first president of the United States. Well, okay, so the Acadian analog would be that Sir John A. Macdonald was the first prime minister of the country. Although the head of state would have been Queen Victoria. Okay, or that semantic memory would be that cats look different from dogs. The other form of memory, as he coined the term, is episodic. The experience of eating a delicious croissant after shopping on the Avenue des Champs-Élysées. Well, that's a French analog. Oh, all right. Tulving was recognized for drawing a distinction between semantic memory and episodic memory. Okay, well, let me run through people's names to see if I can improve my familiarity. I improve my acquaintance with people. Andrew, Husam Andrew. Oh, thank you. Abigail Arsenault. Thank you. Alexander Bullen. Jing Quan Kao. Thank you. Jack Cerrone. Thank you. Quan Jia Chen. Yuja Cheng. Thank you. Carissa Choli. Thank you. Arkaprava Chuduri. Thank you. Siddharth Daga. Daniel Dima. Emil Fredfeld. Justin Futh. Thank you. Sabek Chumami. Charles Griffin. Ken May Grover. Henry Hu. Xiao Hua Huang. Thank you. Joel Kassan. Thank you. Alexander Cole. Chao Sheng Lin. Juan Yi Loke. Yifei Liu. Luke McCutcheon. Thank you. Abu Bakr Mohidin. Oh, thank you. Ruben Navasarja. Jonathan Ing. Thank you. Rishi Prakash. Okay. Syed Mohammed Raza. H.Y. Shi. Larry Tsai. Thank you. Ilan Wang. Hongbo Wang. Saradong Wei. Chikam Wang. Huyan Guzari. Gudarzi. Chen Yi Zhou. Daivin Li. Okay, well, we've been discussing a number of things, and what I like to do, sometimes, a lot of the time, maybe depending on how people react to it, what I'd like to do is cover something, covers some of the basic ideas surrounding something, and then put it down for a while, and then but promising to come back to it. There must be a number of things that we've done that with so far. So one of them, for instance, being the relationship between the two definitions of K0, the module definition and the definition in terms of idempotence. Very roughly speaking, the correspondence is if you have an algebra and you have an idempotent, then if you look at A times E, then that's the left module over A, the left module over A. Okay, so and it's conversely, well, and what kind of a module is it? Well, it's a projective module, and it's singly generated. Okay. Singly generated because every element is equal to something in A times E, and so it's and it contains E because you could take E times E, or if A has a unit, then you can take I guess we're talking about modules. Normally we assume that the algebra has a unit, otherwise you have to adjoin one. And okay, so it's a projective singly generated module, and it's an arbitrary so exercise. Every singly generated projective module over A is exactly equal to A times, or isomorphic to A times E for some idempotent element equal to its square in A. In A itself, you don't have to go to matrices. So so that's an exercise, and then a further exercise is to check what you do with some idempotence in a matrix algebra. How if you have a idempotent in a matrix algebra, what is the finitely generated projective module that it corresponds to it in this natural way, giving you, taking equivalence to equivalence to isomorphism. Well, I'll give you by the way, remember Helmholtz's dictum, Professor Paul Helmholtz's dictum. For every problem, there's an easier problem. Okay, so instead of taking an arbitrary idempotent so take 2 by 2 matrices instead of just n by n matrices, and then we've done 1 by 1 matrices. Take 2 by 2 matrices and look at well, instead of looking at an arbitrary idempotent, okay, well 0 is too easy because 0 module is finitely generated and direct sum of a free module. But let's take the identity. Let's take the unit element. What's the unit element of 2 by 2 matrices over A? Remind me. Remind me of your name. Is that your last name or?
No, it's
Oh, okay. And what is the what's the identity element for multiplication with the 2 by 2 matrices over A? Yeah. So this is A, and now take 2 by 2 matrices over A, and it's an algebra, right? Okay, what was the last word you said?
1, 0, 0, 1.
Yeah. Yeah. Okay, so that's that's the unit of that algebra. Okay, well if that's an idempotent, why don't we try inside A itself, the module corresponding to the idempotent 1 is just A times 1, which is A, and that's called the singly generated free module. The free module with a single generator. Okay, and the reason that A times E is projective is that it is a direct summand of a free module. In other words, there's another module, M, such that AE plus M is well, it's finitely generated free. That means it is isomorphic to a finite direct sum of copies of A. Okay, and as left modules. Okay. So what's M? Yuja, can you tell me what M should be? To get the AE, and how many of these should I take? What's the smallest number? We probably can't do it just with actually maybe we can do it with just one generator. How about just saying if E is an idempotent in A, then can we find a module such that perhaps a submodule of A, such that A times E plus the other module, the direct sum, is isomorphic to A. Yes, Charles? Okay. Did you already know that when you came into this room, or I'm just curious? Sorry? Okay, good. Yeah. So, but okay, well, that's what I like to see. I like to see someone doing a calculation and even telling people what the answer is, even though it might not be right. Okay. The worst thing that could happen is that everyone laughs, right? How bad is that? That I started wearing glasses when I was in grade 3, maybe something like that, and I got them over the Easter holidays, and I was late. I was late. I'll never be late. Well, I can't say that, but Anyway, when I walked into the classroom a few seconds later, everyone everyone laughed. I like to think it was a friendly welcome. Yeah. Okay. All right. Yes. Okay. So Charlie is saying take a e direct sum with a times 1 minus e. And by the way, 1 minus e is also an idempotent, right? If you square that, you'll get the same thing. Try it. And so a times 1 minus e is singly generated. Well, a times anything is singly generated. But it's projective because the a, if you just take plus, don't have to take the direct sum. You look at ae plus some a times 1 minus e, you can put a dot over the plus sign because the intersection is 0. You can call an internal direct sum. And so this is, and it's isomorphic to the external direct sum, which is just abstract. And but then this is easier to calculate because you just prove that ae plus a times 1 minus e is equal to a. Okay. Everyone agree? Okay, you have to remember what it means to add sets. Okay, these are sets. So you take an arbitrary element here, an arbitrary element here, and take the sum. Okay, and that's what the sum is without the dot. And then the dot is just to tell people that whatever the sum is equal to, it's a direct sum. It's an internal direct sum, which is isomorphic to the external direct sum, which means that a times e itself is projective, and that's of course singly generated. Okay, but so now if we look at 1001 in M2A, we want to get this as a module over A. Okay, we want to find a corresponding module, over A, F module. Okay, let's leave that as the next step in the exercise of taking arbitrary idempotents in a matrix algebra, which is what you do to get K0 by the idempotent definition. It's it works just as with a usually you do it with in the textbook it's done with star idempotent, self-adjoint idempotent in a star algebra, but it's similar definition without the star operation, as was shown by Kaplansky. Okay. And for a C-star algebra, you get the same answer. Okay, because every idempotent is equivalent in the algebraic sense to a self-adjoint idempotent. You have to use spectral theory for that. And this is in the book, by the way. It's important for periodicity defined in terms of star algebra, because you need to just look at the Banach algebra to prove about periodicity. And furthermore, if two projections are equivalent in the sense of just of an algebra, if two self-adjoint idempotents are equivalent in the Kaplansky sense, then they're equivalent in the Murray-von Neumann sense. Okay. So that means that the semigroup is the same. The semigroup coming from idempotents and the semigroup coming from projection, self-adjoint idempotents. But this is only not known for an arbitrary star algebra. It's convenient for C-star algebra. It's true for C-star algebra, and so it's convenient to define K0 in terms of projection, in terms of self-adjoint idempotents. But the advantage of this is it works for an arbitrary algebra over a field, or even over the integer, the ring. And it in the important case of the C-star algebra, gives you specialized answer. Okay, so that's one thing we were discussing. What was another thing we discussed? Jack, do you want, is there something else you would like to see, we left the loose end with and might like to see it taken up again? Like, did we finish UHF algebra? Okay, well, of course, I didn't do it. I don't think I actually, I don't remember standing at the board and checking out loud that that Dijk's number theoretical observation. Mr. Lau, Joshua Lau was reminding me that a few years after Dijk's paper, which on UHF algebras, someone else worked out similar the same number theory observation in the setting of solenoids, the topology. Okay, but it was 3 years afterwards. But so there's the basic fact that this has to be it requires heavy arithmetic. Okay, maybe not heavy for me, but heavy for you. Because I learned arithmetic when I was in school. Okay, well, okay, there may be something, maybe a fewer people after me learned arithmetic, but maybe they learned it even better. No. You know, they don't even claim to teach arithmetic anymore. They claim to teach mathematics, but I don't think you can even say that arithmetic is mathematics, not basic arithmetic. Sorry? I'm sorry, I didn't, please don't speak quite so fast. So 50 years difference makes you, I think the language is speeding up, but I haven't.
Do you like how they're teaching math at school now?
Well, I haven't been there for a while. No, I don't know. I don't have children. I have nieces and nephews, but they're great niece and great nephew. Well, okay, but that's sort of changing the subject. I just said something is it's not mathematics, and you asked me about mathematics. You asked me a question about mathematics, but I would say it's not. I mean, one thing that mathematics is important in mathematics is logic. So I'm complaining, right? Okay, but no, it's a pretty diffuse complaint. All right. So so there was this number theory theorem, okay? That so that is mathematics. To prove it, you have to do arithmetic. But so I think you'd say that mathematics is, by definition, mathematics is fun, okay? And which is that which I think we could say excludes arithmetic unless you really enjoy flashcards or something like that, which is what I eventually end up well, if not liking, then not disliking so much. Okay, this was at home. I don't know how I would have reacted to them in school. Okay, so but this is something to check, right? If you have first of all, you always do the easy case first. Follow Helmholtz's. You can save a lot of trouble by picking out the simple case first, because it somehow allows you to organize your thinking with fewer complications. All right. I think in general, it's almost always very good advice. Okay, so what's special case of a supernatural number. Now, I'm going to have to I'm sorry, I'm very slow with names. Very slow. But well, now what was the question? Oh, what's the special case of if we want to show that the supernatural number gives rise to a subgroup of the rational number, then I guess if it's the supernatural number one, we're going to get, what group are we going to get? Yeah, sure, yeah. I didn't catch that because I was expecting you to say the integer.
Oh, yeah.
Okay, I'm sorry, but generally speaking, maybe it's better to avoid mathematical notation when you can, when it's convenient. But that's just an example, okay? I mean, maybe I'm special. Maybe I'm especially slow hearing and catching on. Okay, but okay. So what if you have a general natural number? Then what's the corresponding? I guess it's sort of clear then almost clear what the corresponding subgroup of the rational numbers would be, right? Yeah. Okay.
We discussed it. It was like the 1/.
Yeah. Okay. The notation is helps, right?
Yeah.
So here's a case where it's hard to maybe notation does help. If you say 1/n times z, then that's just ordinary arithmetic, right? If it's an ordinary natural number,
Yeah.
not equal to 0. That's a sometimes it's convenient to include 0 in the counting numbers, natural numbers. Okay, but then does everyone know what to do when n becomes a supernatural number, which is defined in terms of prime factor decomposition, prime power multiplicative decomposition, right? Archiprava, is that you? Okay. Do you know how to do it? If it's supposedly it's 2 to the infinity, then what? Supposedly the supernatural number is 2 to the power infinity. Sorry? Well, so the 2 to the infinity you take with a grain of salt. The important thing is the exponent, which is infinite, okay? But then if it's a finite, if it were a finite exponent just with one prime number, then it would be a natural number. But if it's the infinite power, then what? Well, it's just a convention. Yes. Please say your name again quickly.
Osama?
Uh,
Osama?
Oh, okay, I'll be able to find. I'm very
It's the
sorry.
first one on the list.
It's on the list.
It's the first one.
Oh, okay. Well, then my reading and pronunciation are just very bad. Yeah. Well, looking at the wrong list. Huh. Okay. Hussein Andrew. Yes, Hussein. Sorry. Okay. So what would the group be for the prime number 2 and the exponent and the infinite exponent?
Is it just the infinite direct sum?
Well, I'd say that's a very good guess, but it's because for one thing, the group we're talking about is not going to be finitely generated, okay? And the group you mentioned is not finitely generated, infinite direct sum, okay? But Abigail, would you want to comment on that? Yes, I saw you put up your hand. Okay, so you're suggesting something apparently different, okay? Well then, but then I guess it's a question to prove those two groups are different. Abigail is suggesting that it's a different answer. Now, could conceivably at this stage you could both be right, right? That the groups might be isomorphic. We're just talking about groups. The order relation is not especially well, if it's a subgroup of the rational numbers, then there's a natural order relation. We don't have to talk about it. But we don't. But in Dijksmee's paper, you don't talk about it anyway. Okay. But well, okay. Well, there's something to think about, right? Is it the same group or is it a different one? Pardon? Yes. Okay. Good. That's what I call a lightning computation, and I like to do those, and sometimes they're right. Okay. So, okay. So and so did anyone did anyone manage to take the whole assembly of supernatural numbers and recognize them as a topological space? Shikam? Yeah. Is there a natural topology which is familiar? Of course, every set you can give it a discrete topology, but that is generally maybe that's all you can do in general. But you can hope sometimes to have a more interesting, recognize a more interesting topology. Well, okay, but remember it's sequences of exponents, right? And yeah, that's so you can remember that some of the exponents are 0 and 1, right? And you take infinite sequences of zeros and ones, that's familiar, right? And the infinite product, the Cartesian product, is called the Cantor set, right? But it's not the middle third construction, but it's anyway. Charlie, was that what you were going to say? Sorry. Okay, was that all you were going to say? Yeah, supernatural. Well, okay, but that's okay. We were arguing about discrete. Okay, if it's if it's the natural numbers, then discrete is all you can do, I guess. But don't forget the exponents also possible. Well, natural numbers come in two ways in this setting, and as they come in as special cases of supernatural numbers, but then they're not all there, right? No, they are. They're starting at 1. They're all there. 1, 2, 3, and so on. Those are supernatural numbers. Yes, Chikam?
Define a topology on like the dyadic, the triadic, and so on, and like take a product topology and say that topology on the rational order.
Well, we don't want to mix up between the supernatural numbers and the elements of the corresponding group. So it's if you look at supernatural numbers, then they include natural numbers starting at 1. But then if you look at possible exponents of prime numbers, that each one individually gives you, well, if it's a finite exponent, it gives you a natural number. So, but it starts at 0. So 2 to the 0 is 1, and that's a natural number. And 2 to the 1 is 2, and so on. And then the difference with the exponents is that they're not just natural numbers starting at 0. You're also allowed to have infinity. So the exponents, the exponents are discrete, right? The finite exponents are discrete, but the infinite one is piled on as a limit in a natural way, right? If you take that topology on the when we talked about the infinite product, when you speak when you were discussing, when you were suggesting the infinite product of sets, then for the just 0, 1, you take the discrete topology. But if you take the going 0, 1, 2, 3 up to infinity, it's not the discrete topology. You take the topology where the isolated points converge to the point of infinity. But that's totally disconnected. That's totally disconnected. And if you take infinite product of copies of that, then it'll be still totally disconnected. And if it's metrizable to begin with, it's compact and metrizable to begin with, it'll be compact and metrizable afterwards. And yeah, but there's one more thing you have to check to show that it's the Cantor set, okay? What's that? Jack, what do you need to check to, Abigail, what do you need to check to get that a totally disconnected compact metric space is the Cantor set? Are you familiar with that characterization of the Cantor set? There's one property, one additional property you need. For instance, to take a single point, that's not the Cantor set, is it? Right? Well, that's better. That's close, but I'm sure it doesn't include some things. Yes, Jack, do you have that at your fingertips? Well, okay, but that dense is something that applies to a subset, right? But it doesn't necessarily apply to the whole, just to a whole space. If it's a subset of a metric space, then you can say it's dense, or of a topological space. That means the closure is everything. But well, there's another way of saying dense too. That order theoretically, you say that any 2 points have something strictly between them. Yes. Well, it's compact and metric space, so it's automatically complete. Okay, that's good. But so yes, Archiprava. Sorry. Well, okay, but I think I may have mentioned that because the original set is totally disconnected. Any Cartesian product of copies of it will be totally disconnected, and also compact if it's compact. But you've got to exclude it being a single point, but you've got to go just a little farther than that. If it's you want to exclude it as 2 points, for the. Okay, well, okay, well, I'm not going to. I don't think I'll let the cat out of the bag. But this is a good exercise. Okay, it's kind of fundamental, not just in C-star algebra theory, but so the point is that if you take a totally disconnected compact metric space, then with a very simple additional condition, it has to be the Cantor set. Now, it will imply that it's uncountable, but Miguel suggested, but it's not. That's not. I don't think that's strong enough restriction. Yes. Well, compact, very good, but that's automatic if it's compact metric. Okay, compact metric spaces has a countable basis of open sets, or it has a countable dense set. For metric spaces, that's equivalent. Okay, so let's just leave that as something to think about. Yeah. Yeah. What's the difference between if you look at compact metric spaces that are totally disconnected, then a priori there are many of those. Okay. And most of them are uncountable. But the question, which one is it possible to single out by a simple property? Which one of them is the Cantor set? Jack, do you remember that? Yeah, it's something you have to remember, or it takes a while to figure out. Okay, well, I'm guessing you're remembering that now. Okay, good. No, good. No. Okay, but it's an impolite question, but I'm just curious. I'm curious about things like that. Because it would be, I think, I wasn't expecting anyone to work it out, okay? It's a somewhat subtle fact. Well, somewhat, rather subtle fact. Uh, and it's something that's so elegant that it's a single condition which eliminates all of these compact total disconnected metric spaces except just a single one, okay? Maybe the single one is a key, a memory key. Because the extra condition is the single isolated point, okay? And it should not be there, which excludes the case that the whole thing is a single point, right? For instance. That's very elegant. And if you want to put it in as an exercise, that's fine. The proof. I mean, it's you may have to work a bit to work it out, to have a bit of arithmetic probably. Okay. So what's there was the the UHF algebras, which are parameterized by this Cantor set, very nice space. And and then there's the isomorphism classes. Well, that's exactly, it turns out it's exactly the same thing, right? You have how many boards are there? Well, so you have a, if you look at supernatural numbers as a category. Well, this is I brought this chalk. I'm responsible for it. It's doesn't write very well. I hope it erases. Okay. So this is a category, and the arrows are n divides n prime. Okay. Meaning the exponents are larger. The prime each corresponding exponents get larger. Okay. And then look at UHF. So there's a natural construction. You have the supernatural number. That means you have the exponents. So you look at m to the 2 to the e2. E2 is the exponent for 2. Tensor 2. Sorry. Yeah. And then tensor m3 to the e3, the exponent for prime number 3, and so on. This is an infinite algebraic tensor product, the increasing union in a natural way. And if you have, so you have the largest one where all the exponents are infinite, and then if some of the exponents are finite, you just take the first finite number of them. I mean, so if it's, in other words, you write this as m2 in certain. Well, it's contained in this one is contained in m2 to the infinite number of times. And if you have a larger exponent, so you take, by definition, you take the first e2 of them, okay, and a larger exponent then will give you a larger algebra, larger subalgebra. Okay, so it's a functor. So the arrows here are unital homomorphism. Okay, those. So that's a functor between categories. And then UHF turns out that you can recover, almost recovering the supernatural number immediately, but the easiest way is to do it with the group, okay? So groups containing the integers, as Husam said, and contained in the rational numbers, okay? And so so the special case Mn, it is a functor, but it has the property to take Mn into what? What does who was Jack? Was it you that reminded us of the notation for the group? Who was it? Husam, was it you? Okay. So and it was 1 over n times z, right? Yeah. Okay. So Mn goes to 1 over n times z, and it's defined for arbitrary algebras, including anything isomorphic to Mn, where you've forgotten the n. Okay, you just know it arises as a UHF algebra. It's isomorphic to one of the Mn's, but then so somehow you get the n coming out of the blue. Okay, because this group immediately tells you what n is. The last functor is going back here. Okay, and that's just the one-to-one correspondence, bijective correspondence between the groups and the supernat. Okay, so we were discussing that, and also there's the free floating version of it. Okay, and Fanny, I remember you sent me an email questioning what the purpose of the free floating algebra was based on a given algebra, and and in particular, what's the purpose of a free floating algebra? What's the purpose of having an algebra which is isomorphic to its own free floating algebra? Well, so by the way, if it's a free floating algebra, the infinite matrix algebra based with entries in a given algebra, then it's always free. It's always isomorphic to just take that algebra and take the free floating algebra over it. Then you don't get anything new. It's the free floating algebra over a free floating algebra is the same algebra up to isomorphism. That's a good exercise. So if infinite cardinals, working with infinite cardinals, says that L of 0 times L of 0 is L of 0. But so the but if you look at a unital algebra, then you take the free floating algebra, won't be unital. So you free floating algebra of the UHF algebra will not be UHF. And in fact, the classification in this particular case, the free floating algebras have a wilder classification than the free floating ones. It's not supernat. It's several different ends will give you the same free floating algebra, and that's a very good exercise. Okay, but the main point of the so the free floating in that setting, the free floating algebras are worse. They're worse than the ones they're based on. Okay, because the ones they're based on, the isomorphism is very smoothly parametrized. Isomorphism classes just by supernat. But it's a slightly tricky exercise to look at the equivalence relation on supernat. It amounts to saying that corresponding UHF algebras are isomorphic, and it's in fact these free floating algebras are better to work with in general, because even if something is not free floating in general, it's never going. The isomorphism classes of a certain class of algebras, for instance, the AF algebras, even simple unital AF algebras. These are special cases of simple unital AF algebras, but they're very, very well behaved. Arbitrary simple simple unital AF algebras, they're already badly behaved, okay? In the sense that the isomorphism classes are wild. And so the if you take a look at the free floating algebras based on these, they're not any worse. And in fact, they're better because already for these you need the K0 functor. It's not, you don't just have a group. I don't have a subgroup of Q, a specific subgroup of Q. You have a functor, okay? You have an abstract group, abstract ordered group for simple unital AF algebras. And in addition, you have to carry along the class of the unit as an element of this ordered group. But if you take a look at the free floating algebra, there's no unit. So that sounds bad, but that means what that means in practice is that you don't need to worry about any unit. So if you look at the K0 group, it's just an ordered group. You don't need to keep track of any of the class of the unit. And that's a much simpler and better thing to look at. For instance, here's an example of why it's better. So already in the case just of Q, okay? So instead of looking at the invariant, including the one, then there are no automorphisms, okay? No automorphisms of this group, which fix the point one. If an automorphism, a group automorphism of Q, it fixes the point one, then it has to be the identity. But in general, if you pass to the free floating algebra and look at the K0 group that you get, so this is K0 of a certain UHF. But if you just look at Q itself, then this is K0 of a free floating algebra. Okay. And there are automorphisms of this, and they come from automorphisms of the free floating algebra. Okay. You can multiply everything by 2. And so that's and so in the free floating algebra, if you look at the trace and you do the automorphism of Q, multiplying it by 2, that's a group automorphism, right? Then that will multiply the trace by the number 2. You have an automorphism that shifts the trace, it changes the trace, which is very useful in applications. Okay, so that's a brief review of some of the things we've discussed. And I'd like to think that they form a good basis for exercises or even essays. So something else to review is the proof of the classification theorem. The proof of the classification theorem for AF algebra, AF isomorphism theorem. Remember, if you have two inductive limit sequences, I had an intertwining of the K0 groups, and then I lifted each of the arrows to arrows between the algebras. Okay, and then I changed the arrows. Each arrow I changed once to have the same action on K0. That's how I managed to change it. But I changed each arrow once to get a commutative diagram. Okay, once it's a commutative diagram, then you get an isomorphism with a limit between the algebras, instead of just one between the so this is between the algebras. So just the dotted line means they exist. You get them, and solid line means you're given them. Okay, well that's okay. I've done it again. Okay, I mean, yeah. Well, everyone can walk out now. Okay.